Hello everyone, I'm Norman Wildberger. In today's famous math problem, we have a rather special situation because we're treating the most fundamental and important problem in mathematics, at least in my opinion. Natural question that will be on your mind is, what is this most fundamental and important problem? And I think it's part of my duty here when laying out all these different problems that we're going to be looking at. Some of them are interesting, some of them are curiosities. They range over a lot of different territory. So it's nice to have that aspect, but it's also nice to have an idea of the relative positions of problems, in particular to identify clearly which are the most fundamental and important problems. So this is a real core problem that we're talking about today. It's fundamental in the sense that it lies at the base of mathematics. It has a sort of elementary aspect and also a wide-ranging aspect. It affects a lot of different mathematics at a very foundational level. It's important because, first of all, it connects with many areas, but we'll also see that it crops up historically in a lot of different places. A lot of famous mathematicians have, at some point or another, wrestled with this problem, or some aspect of it. And it has lots of consequences. So the way we answer this problem affects a lot of different mathematical theories. All right, so without more ado, little drum roll. The most important and fundamental mathematics problem is, well, here it is. Famous math problem number 19. How to model the continuum. How do we get into mathematics the idea of continuity? In particular, how do we model the continuity that we see when we look at a line? Now, this is a rather open-ended problem, and the difficulty level is ranging over a wide range. At some level, it's a solved problem, and we're going to talk about that aspect of it today. Difficult, but not overly difficult problem with a level of 4. And it goes up to very, very difficult problems, perhaps ultimately unsolvable problems. So there's a wide range of possible answers to this problem. It goes back, of course, historically, to the ancient Greeks at least, to the work of Pythagoras, to the paradox of Zeno, to the work of Eudoxus. It was also very great interest to Archimedes, to Aristotle, and other thinkers. This problem lies at the heart of geometry and analysis. But in fact, it also has a lot to say about modern algebra too. It's intimately connected with physical questions, having to do with time, quantum mechanics, even the large-scale structure of the universe. These days particularly, it's intimately tied up with set theory and axiomatic approaches to mathematics, some of which I think are rather problematic. The question is really a basis for a lot of more advanced disciplines in mathematics, in pure mathematics especially. Algebraic topology, differential geometry, algebraic geometry, linear algebra. In fact, a lot of areas. I could have listed more here, aside from, of course, geometry and analysis. And very interestingly and prominently, this question connects with modern computer science. We'll see that as we progress a little bit later more deeply into the question. I believe this is a fundamental kind of open-ended problem that's not going to go away. Really, really important problems can never be fully solved. We can make progress towards them, but there's always something more that unfolds as we learn more. I believe that in 1,000 years from now, this will still be a core problem. In fact, it still may be the most important and fundamental problem in 1,000 years. One very interesting aspect of this problem is that nowadays, around the year 2014, this problem is largely invisible to most math students and, in fact, most mathematics professors. That's because the modern pure mathematician largely believes that this problem has been solved. This is an erroneous idea, but it's a very common one. They think that the continuum is modeled by the so-called real number line. They think that there is something called the real number line, and that answers the question of what the continuum is. The real number line is usually presented in a picture, something like this, with integers and fractions placed where you would expect, and sort of arrows pointing to particular so-called irrational numbers like root 2 or e or pi. But the actual specification of, first of all, these irrationals and their arithmetic and the proofs of the laws of arithmetic of these so-called irrational numbers is rarely laid out completely. There's various sort of cliches that people learn. Students learn to recite the statement that a real number is an infinite decimal, or perhaps a Dedekind cut, or perhaps an equivalence class of Cauchy sequences, and there are other possibilities too. But when you actually look carefully, try to find a place where the theory of any one of these is clearly laid out, well, then the logical problems become pretty obvious. So it's a very unfortunate aspect of modern mathematics, and it's a very big step for students to start appreciating that the status quo, the orthodoxy that they have been taught, is in fact really misleading and misrepresents the historical importance of this absolutely crucial question. So the modern orthodoxy is in fact seriously in logical error. Now, this is a very important issue, of course, and I deal with it and am dealing with it at length in my Math Foundation series. And I don't have time to summarize everything there in a few lectures here, but I am going to give you an overview of some of the logical problems. But I'd like to emphasize that you can test this for yourself. Okay? So the way to test it for yourself is to actually look for a place where the theory of real numbers is properly laid out, and then actually read it. Okay? It's remarkable that if you open most calculus texts, and for most calculus texts, the real number line is the absolute fundamental framework on which modern analysis is built. But you look for a chapter that lays out the arithmetic of real numbers properly and carefully and completely, and uniformly you will find such a chapter missing. There will be references to it. There will be some quick statements that summarize some of the things that hopefully are true about real numbers, but for an actual complete laying out, you will not find it. A few years later, when you graduate to a course in modern analysis, the same situation arises in modern analysis texts. And you can check this out for yourself. You can open up modern analysis texts and look for the chapter on the theory of real numbers. There almost never is such a chapter. Occasionally there's something in an appendix. Then when you look carefully at that appendix, you see that as you look more and more carefully, the logic starts to recede. That you start noticing that they're already assuming things that are pretty close to being what they're supposedly constructing. We're going to talk a little bit more about that, but you can check it out for yourself. That's the point. You don't have to take my word for it. Open up the book, see where is the theory of real numbers, where it's properly laid out, what the actual objects actually are, how you do arithmetic with them, in other words, proper definitions of the operations, and then proofs of the laws of arithmetic. I claim nowhere on planet Earth in the year 2014 is such a thing laid out, which makes a lot of the mathematics that's built on the real numbers a logical sham, if I'm going to be completely honest. All right? I mean, honesty is what I'm sort of interested in here. It's a logical sham. And it's an unfortunate situation, so one of the things I hope to do here is to convince you that this is, in fact, an open-ended problem. It's still an open problem. There's still more to be done. There's a lot of connections with computer science that we need to understand before we can really get at a grasp of what this problem is doing. But, on the other hand, there is also a solution that already exists. There is a solution to the problem that already exists, a very workable basis for mathematics that goes back, of course, to the ancient Greeks. So the history of the subject is intimately connected, and we are going to have a lot to say about the development of this interesting question, and I hope that in the next few videos you're going to learn quite a lot, not just about this question, but also about associated and related areas.